This is Calculus 2 video lecture number 4 on integration of rational functions by partial fractions. So this method will be used on integrals whose integrand is a rational function, and the method of rewriting a rational function into a sum or difference of rational functions is called partial fraction decomposition. I'm just going to give a brief review of how to do partial fraction decomposition. It should have been a topic that you covered in Precalculus. If not, or if you feel like you're a little bit rusty, then I'm linking up here a video going over the different cases and how to do partial fraction decomposition. So be sure to check it out if you need a refresher or if you never even saw it to begin with, because I do go step by step. So here's how you want to tackle these integrals. The first thing is you look at the integrand, it's a rational function, and if it's an improper fraction, meaning the degree of the numerator is greater than or equal to the degree of the denominator, then you need to divide the denominator into the numerator by using long division of polynomials. If you forgot how to do that, have no fear. I have another video on how to do long division with polynomials. I'll link it right up here for you. The result will have the form f of x, that's your quotient, plus little r of x, that's the remainder, divided by q of x. So what you would do from there is factor the denominator, capital Q of x, into a product of linear factors or irreducible quadratic factors, and then collect the repeated factors. And then you're going to apply the following rules to the factors that you find in the previous step. So basically, you're going to deal with integrating f of x the way you would any polynomial, and then you're going to apply partial fractions to the remainder if you have one. Okay, first case, here we go. The denominator is a product of distinct linear factors, in which case you solve for each of the constants, a1 through am, if there's m factors, where each numerator, a sub k, is a real number. This will make more sense when you see an example, so let's just do one. Here we go. So evaluate the following integral. I have 1 over x plus 4 times x minus 1 dx. So first we're going to find the partial fraction decomposition for 1 over x plus 4 times x minus 1. So this is the first case. I have a product of distinct linear factors in the denominator. So the decomposition will have the form a, some constant, over one of the factors, x plus 4, plus b over the other factor, x minus 1. My goal is to solve for a and b. So to do that, I want to first clear out the fractions in this equation. So I'm going to multiply by the LCD, which is x plus 4 times x minus 1. And now I'm left with 1 equals a times x minus 1 plus b times x plus 4. Now there's two main techniques that you can utilize when you're solving for a and b, and I'll show each one as I solve the different examples. So one technique is we're just going to distribute everything out. So I have 1 equals ax minus a plus bx plus 4b. Now in order to solve for a and b, what I need to do is collect the like terms together. So basically I want to figure out all of the terms that are linear, that have x to the first power. If I focus just on those, on the left-hand side of the equation, I don't see any x's. So basically I have 0x plus 1. That means 0x must equal ax plus bx. Or if I just focus on the coefficients, that means 0 has to equal a plus b. I'm going to do the same thing with all of the constant terms, the terms that don't have any variables in them. In this case, 1 is a constant on the left-hand side of the equation, and then negative a, there's no variables attached to that, and 4b are also considered constants. So 1 has to equal negative a plus 4b. And now I'm in a good place because I have a system of two equations with two variables, and I can easily solve this by elimination. Adding the two equations together, I get 1 is equal to 5b, which means that b is equal to 1/5. All right, lovely. And then notice here, since a plus b equals 0, if b is 1/5, then that means a has to equal negative 1/5. And now we're ready to roll. So I'm going to rewrite my original integral, this time using the partial fraction decomposition for the integrand. So I have integral of, a was -1/5, so I've got -1/5 over x plus 4 plus +1/5 over x minus 1 dx. All right. I'll take this one step by step, and then once you get the hang of it, you can kind of go a little more quickly. So I can take the constants outside the integral, and I'm actually going to split it up for you guys just this time. So I have -1/5 times the integral of 1 over x plus 4 dx plus +1/5 times the integral of 1 over x minus 1 dx. All right, and then each of these antiderivative is going to be natural log of the absolute value. First one's going to be x plus 4 plus, then I have 1/5 natural log absolute value x minus 1 plus c. Now I can clean this up a wee bit. I can factor out 1/5 from both of the natural logs, and I'm actually going to put natural log of x minus 1 first because that one's positive, and then minus natural log of x plus 4, and then I have the plus c hanging out there. And then remember, with our properties of logarithms, I can rewrite subtraction of two logarithms using division and rewrite it as a single logarithm. So now I have 1/5 times the natural log absolute value, x minus 1 over x plus 4 plus c. Beautiful. Now you could move that 1/5 to the exponent on the argument, or you could just leave it as is. Ooh, come on. We're very proud of this one, but it refused to be boxed, so we're just going to compensate like this. All right, so there's our final answer. That's case 1. That's the most straightforward case. Okay, case 2, are we ready? Here we go. Case 2, the denominator is a product of linear factors. Some of each are repeated. So basically, some of the linear factors may be raised to higher powers than the first. They might be repeated. So what does the setup look like? Well, I'll show you right now. So say you have the following integral, x squared minus 5x plus 16 over 2x plus 1, and then here's the little problem child that puts us in case 2. We have x minus 2 squared. So how do you deal with this? Okay, check this out. So you have x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared. So it starts off the same. You have a over 2x plus 1 plus I have b over, I have to start off by listing x minus 2 to the first power, and then I have c over x minus 2 squared. And I stop because that's the highest power that I see in the denominator. If it had been x minus 2 cubed, I would have had to add plus d times x minus 2 cubed. So you have to start at the first power and then increase the exponent by 1 until you hit the highest exponent you see on that factor in the denominator. Okay. Then from here, the rest is pretty much the same. So you're going to clear out the fractions. We're going to multiply by the LCD. In this case, it's 2x plus 1 and x minus 2 squared. Just the LCD, don't overdo it. And then we're going to have x squared minus 5x plus 16 is equal to a times x minus 2 squared plus b times 2x plus 1 times x minus 2 plus c times 2x plus 1. Now I'm going to show you the other technique that we can use to solve for, in this case, a, b, and c. And the idea is you're going to let x equal some value that's going to cancel out a bunch of terms. The first one that I'm going to choose is I'm going to let x equal 2. Why did I pick that? Because that's a 0 of this factor here, and things are going to work out really nicely. So I'm going to substitute 2 in for x everywhere in this equation. So on the left-hand side, I'm going to have 2 squared minus 5 times 2 plus 16 equals a times 0 plus b times, who cares what 2x plus 1 is going to be? It's b times 0. That's all I care about. Plus c times 2 plus 1. All right, so on the left-hand side, we've got 4 minus 10 plus 16, that's 10, equals, a is gone, b is gone, I have 5c. So bam, I know right off the bat, c is equal to 2. Very nice. Okay, that was so fun. Let's see if we can do it again. This time, let's let x equal negative 1/2. Okay, so we're going to let x equal negative 1/2. That means we'll have negative 1/2 squared minus 5 times negative 1/2 plus 16. That's going to equal a times negative 1/2 minus 2 squared plus b times 0 plus c times 0. Okay, so what do we got on the left-hand side? That's negative 1/2 squared, so that's positive 1/4 plus 5/2, so plus 10/4 plus 16, which is 64/4. So we've got altogether 75/4 on the left-hand side. And then negative 1/2 minus 2, that's negative 5/2. If I square it, that becomes 25/4 as the coefficient on a. All the other terms go to 0. Ooh, this is looking good. So that means a is equal to 3. Yes? All right, now what to do, since I still need to find b, I could multiply it all out and group the terms like we did in the last problem, but we already know a and c. So just pick some other number to plug in for x, and then we can substitute in what we know a and c are equal to and find b. So what's a nice number that you're in the mood to plug in? How about 0? I like 0. Okay, we're going to plug in 0 for x. And let's see what we have here. So we'll have 0 squared minus 5 times 0 plus 16 is equal to, now I know a is 3, so this is going to be 3 times 0 minus 2 squared plus b times 2 times 0 plus 1 times 0 minus 2 plus, and then remember we know c is 2, so this is going to be 2 times 0 plus 1. All right, so on the left-hand side, I only have 16. And then on the right-hand side, this is going to be 3 times positive 4, so 12. And then I have 1 times negative 2, so minus 2b plus 2. All right, so that's 14 on the right-hand side. 16 minus 14 gives me 2, so 2 equals negative 2b, which means b is negative 1. Good. So now let's put it all together. Remember, originally we needed to integrate x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared dx. And now that we found a, b, and c, I can rewrite this as 3 over 2x plus 1 plus negative 1, that's b, over x minus 2 plus 2 over x minus 2 squared dx. All right, now each of these we can actually integrate pretty easily. So the first one, don't actually do a u-sub. Hopefully at this point in your calculus career you can look at it and say, if I were to let u equal 2x plus 1, du would be 2 dx. So I'm just going to pick up an extra 1/2 in there, okay? So we'll have that 3 and the 1/2, and then you have natural log of the absolute value of 2x plus 1. Same thing for the next one, right? Just minus natural log absolute value x minus 2. And then don't forget here, this is 2 times x minus 2 to the negative second. So increase the exponent by 1, divide by the new exponent. Now you're going to have negative 2 over x minus 2 plus c. Good stuff. From here, I would want to move this 3/2 to the exponent on 2x plus 1 so I can combine those logarithms, and make sure you keep the absolute value. So we'll have natural log absolute value of 2x plus 1 to the 3/2 over x minus 2, and then you have that one extra term hanging out there, minus 2 over x minus 2 plus c. And now we're done. Okay, so that's case 2 for a repeated linear factor. If the process of partial fraction decomposition is kind of overwhelming to you, then stop this video right now, go watch the partial fraction decomposition video for pre-calc, and make sure you have that under control. Here we go, case 3. There's only 4 cases, so don't fret. The denominator has distinct irreducible quadratic factors. Then the expression will have a term of the form ax plus b over ax squared plus bx plus c. I'll show you exactly what I mean by that in the next example. So we're going to evaluate the following integral, 3x squared plus x plus 4 over x to the 4th plus 3x squared plus 2. So let's dive right in. We've got 3x squared plus x plus 4 over, now let's factor the denominator. It's going to factor into x squared plus 2 times x squared plus 1. Now notice I can't factor any further. X squared plus 2 and x squared plus 1, those are sums of squares, so they're completely factored as is. What do I do in that case? Well, I have to have an ax plus b in the numerator for each of those factors. Basically, if the denominator is an irreducible quadratic, then you have to have a linear expression in the numerator, ax plus b. Plus, and then the next term has x squared plus 1 in the denominator, which is also an irreducible quadratic. So I need cx plus d in the numerator. And then if I had another one, you would have ex plus f, and so on and so on. Okay, now let's clear out the fractions from the equation. So I'm going to multiply by x squared plus 2 and x squared plus 1. And now I have 3x squared plus x plus 4 is equal to ax plus b times x squared plus 1 plus cx plus d times x squared plus 2. Okay, the method that I used for the previous example won't work because there are no zeros for x squared plus 1 or x squared plus 2, right? They only have imaginary roots, so that won't work. So we have to use the first method that I showed where we distributed everything out and then collected the coefficients from like terms. So we have here 3x squared plus x plus 4 equals ax cubed plus ax plus bx squared plus b plus cx cubed plus 2cx plus dx squared plus 2d. Okay, the highest power of x I see is x cubed in the whole equation. On the left-hand side, there's no x cubed, so 0 equals, and then let's see here. There's an ax cubed and there's a cx cubed. So 0 has to equal a plus c. Okay, moving down, next is x squared. The coefficient of x squared on the left-hand side is 3. On the right-hand side, we have a bx squared and a dx squared. So that means 3 is equal to b plus d. Next would be x to the first, our linear term. So x has to equal ax plus 2cx. So 1 has to equal a plus 2c. And then lastly, your constant terms. So on the left-hand side, we've got 4 equals b plus 2d on the right. So 4 equals b plus 2d. All right, now notice the first and third equations only involve a and c. If I subtract this first equation from the third one, a cancels out, and I just get 1 is equal to c. So that means c is equal to 1. And if c is equal to 1, then that means a equals -1. All right, and then the second and fourth equations only involve b and d. Same thing, I can subtract this equation from the fourth one. B will cancel out, and then you should get 1 is equal to d. And if d is equal to 1, then that means b is equal to 2. All right, so let's put everything together now that we found a, b, c, and d. So we have the integral of a was -1, so I have -x, b was +2. That goes over x squared plus 2, plus I have x plus 1 over x squared plus 1 dx. Okay, what to do from here? I'm actually going to split each of the terms in the numerator once more so you can see. We're going to have integral of -x over x squared plus 2 plus 2 over x squared plus 2 plus x over x squared plus 1 plus 1 over x squared plus 1 dx. All right, now let's talk about how we would integrate each of these. First one, notice the degree of the denominator is 1 degree higher than the degree of the numerator, so that's just asking for a u-sub. That'll be number 1. The second one, you should recognize this. It matches our form for tan inverse. That'll be the second one that we do. Third one, again, very similar to the first one, we're going to do a u-sub. And then the fourth one, again, that's going to be a tan inverse. That's actually exactly tangent inverse of x. Okay, so I'll do them one at a time off to the side here. So aside, integral number 1. We're going to look at -x over x squared plus 2 dx. So what we will do is let u equal x squared plus 2. Then du is going to be 2x dx. So 1/2 du is equal to x dx. So now rewriting this in terms of u, I have -1/2 integral of 1 over u du. And then this gives me -1/2 natural log absolute value of u plus, I'll call this C1. Okay, you'll see why in just a second. It's going to be so nice. And then I'll rewrite this now as -1/2 natural log absolute value x squared plus 2 plus C1. Okay, so that's on hold. That's the result from number 1. Okay, time for integral number 2. 2 over x squared plus 2. So we have integral 2 over x squared plus 2 dx. Now this is one you just need to put to memory, all right? Anytime you have x squared plus a squared in the denominator, it's going to involve tan inverse. In this case, a is equal to rad 2. And then this coefficient of 2 is just going to come along for the ride. So we have 2 times 1 over a, so 1 over rad 2, and then tan inverse of x over rad 2, x over a, plus c2. And then 2 divided by rad 2, that simplifies, that's just rad 2 times tan inverse of x over rad 2 plus c2. Okay, this one's on the back burner now. Integral number 3. Do you remember what it was? Don't worry, I do. Or you could rewind. So it's x over x squared plus 1 dx. So notice in this one we have x to the first in the numerator, not just a constant. That's why it's not tan inverse. That's why it's time to do a u-sub. And we're going to use the same u-sub as before. So we're going to let u equal x squared plus 1. Then du will be 2x dx. So 1/2 du is x dx. And then now I have 1/2 integral u over du, and then hopefully by now we can just jump to this is 1/2 natural log absolute value x squared plus 1 plus c3. Yes. This is also on the back burner now. Last one, integral number 4, the easiest, breeziest one of all. We just have integral of 1 over x squared plus 1 dx. Nothing fancy going on. A is exactly equal to 1. So this is tan inverse of x plus c4. You guys, that's it. We got to just put it all together. Now clean it up. So all together, everybody, we have negative 1/2 natural log. You know, I don't need absolute value on x squared plus 2. That's always positive. So I'll just switch it to x squared plus 2. Plus rad 2 tan inverse of x over rad 2 plus 1/2 here natural log. Again, I don't need absolute value. X squared plus 1 is always going to be positive. Plus tan inverse of x plus c. I'll define what c is in a hot second. Let's just clean this up a little bit because I notice both these natural logs have a coefficient of 1/2, so I want to factor that out. And then I have natural log. I'm going to put x squared plus 1 first, minus natural log x squared plus 2 second, plus, and then rad 2 tan inverse of x over rad 2 plus tan inverse of x plus c. And we're almost there. I just want to combine these two logarithms, right? Combine their arguments using division. Express it as a single logarithm now, so I have 1/2 natural log x squared plus 1 over x squared plus 2 plus rad 2 tan inverse x over rad 2 plus tan inverse of x plus c. And then you have to tell everybody what this c is. I mean, they're not mind readers. Where c is equal to c1 plus c2 plus c3 plus c4. Oh, this is just lovely. We're going to box it with pride. Very good. Okay, so you can see that you don't get to forget any of your integration techniques as you learn new ones. They actually come together really beautifully throughout the rest of your calculus career. Okay, we have one final case. Are you ready for it? Any guesses? Case 4. The denominator contains a repeated irreducible quadratic factor. What in the world? So you're going to treat it the way you treated a repeated linear factor. It's just now in the numerator you have to have a linear expression. So ax plus b, cx plus d, etc., etc. So we've got an integral x cubed plus 2x squared plus 3x minus 2 over x squared plus 2x plus 2 quantity squared dx. Notice x squared plus 2x plus 2 cannot be factored, at least not over the real numbers. So it's an irreducible quadratic and it's repeated. Let's find the partial fraction decomposition. We have x cubed plus 2x squared plus 3x minus 2 over x squared plus 2x plus 2 squared equals. So remember, you start off by listing that factor just to the first power, and then you work your way up. So we have ax plus b in the numerator because it's a quadratic factor. And this is going to be x squared plus 2x plus 2 down here. Plus, now I have cx plus d over x squared plus 2x plus 2 squared. All right, now let's clear out those fractions. So I'm going to multiply by the LCD, which in this case is x squared plus 2x plus 2 squared. And let's see what we get. We have x cubed plus 2x squared plus 3x minus 2 equals ax plus b times one of those x squared plus 2x plus 2's is going to cancel. So I've just got x squared plus 2x plus 2 plus cx plus d. Again, for these irreducible quadratics, you just have to multiply them out because nothing will make the factor equal 0. So we have x cubed plus 2x squared plus 3x minus 2 equals ax cubed plus 2ax squared plus 2ax plus bx squared plus 2bx plus 2b plus cx plus d. Okay, let's start collecting like terms. So x cubed. I see an x cubed over here. I have an ax cubed. That's it. Ooh, okay. So a has to equal 1. Now let's move on to x squared. I've got a 2x squared here, a 2ax squared, and a bx squared. So that means 2 must equal 2a plus b. Well, I already know a is 1. So if a is 1, then b has to be 0. See, even though these look really scary to start off with, typically solving them is not so bad. All right, moving on to x. 3x equals 2ax plus 2bx plus cx. Okay, so that means 3 has to equal 2a plus 2b plus c. But remember, we already know a and b. A is 1, b is 0. So that means c has to be 1. Nice. And then constant, we've got -2 has to equal 2b plus d. Cool. But we know b is 0, right? So therefore d is -2. Okay, let's put everything together now. So we have the integral of x over x squared plus 2x plus 2 plus x minus 2 over x squared plus 2x plus 2 squared dx. Okay, so let's start thinking about our strategy, because this is a little different than the previous example where we had to do a u-sub. Because notice, the degree of the denominator is indeed 1 degree higher than the degree of the numerator. So you might think, yeah, I'm going to do a straight old u-sub. And you're right, but we have to apply a little twist. So if u is x squared plus 2x plus 2, then du would be 2x plus 2 dx. And if I factor out that 2 and divide by it, that means 1/2 du is equal to x plus 1 dx. But I don't have x plus 1 in that first term. I just have an x. So what do? In math, when you don't have what you want, you don't sit around feeling sorry for yourself. You just make it happen. So you go, oh my goodness, I wish in the numerator I had an x plus 1. That way my u-sub would work out so perfectly. So I'm going to make it x plus 1. But if I added 1 in the numerator, I have to subtract 1 also, right? That way I'm not just messing with the original expression. Everything's mathematically sound. Plus, and then we're going to actually apply the same u-sub for the second integral because we have that same expression in the denominator. It just happens to be squared, but that just means you're going to have a u squared in the denominator again. Okay, so what does that mean for us? Well, again, I want there to be an x plus 1 in the numerator. So how would I make x minus 2 into x plus 1? How much would I have to add? I would need to add 3, correct? So I'm going to take x minus 2 and add 3, and then I'm also going to subtract 3 in that numerator. And then this is all over x squared plus 2x plus 2 squared dx. All right, this is just getting things set up for us. We're not in the nitty-gritty of it just yet. All right, here we go. So we're gonna group this first integral into x plus 1 over x squared plus 2x plus 2. That's the first one. X plus 1 over x squared plus 2x plus 2. And then I have minus 1 over x squared plus 2x plus 2. That's this guy right here. Plus, and then remember, this is all x plus 1. So I've got x plus 1 over x squared plus 2x plus 2 squared for this denominator. So there he is. And then minus 3 over x squared plus 2x plus 2 squared, close it up, dx. So again, we've got 4 integrals to tackle. Let me draw the arrow for this one so you know where he went, down here. And let's talk about what we're gonna do first. Let's strategize. So we know this one we set up so that we could do a u-sub. That's integral number 1. Integral number 2. Integral number 2, we're going to use a trig sub. All right, integral number 3, another u-sub. And integral number 4, you guessed it, constant over some quadratic expression, it's trig sub time. Okay, just think it's like how we used tan inverse in the last problem when you had a constant over a quadratic. Same idea. The u-sub won't work because there's no x to the first power in the numerator. So you have to go to trig sub. Also be super careful because there's minus signs on integral 2 and 4. So don't forget to subtract them. Okay, here we go. Integration party time. Integral number 1. We've got x plus 1 over x squared plus 2x plus 2 dx. Remember, we did all the prep work for this already because we created this perfect scenario. Since u is x squared plus 2x plus 2 du, well, we already know 1/2 du is x plus 1 dx right here. So we're going to have, take that 1/2 outside for crying out loud, integral du over u, and this is going to be 1/2 natural log absolute value x squared plus 2x plus 2 plus, you guessed it, C1. Okay, that's done. Going on the back burner to simmer. Do you guys watch cooking shows? That's where that comes from. You know when the chef has like 5 different saucepans going on and one he puts on the back burner to simmer? That's what we're doing right now. Okay, trig sub time. Don't forget this one we're going to have to subtract. So we have integral 1 over x squared plus 2x plus 2 dx. Perhaps you remember from the video on using trigonometric substitution. If you don't, I'll link it right here. We're going to complete the square in the denominator. So we have x squared plus 2x plus 1, which I can factor into x plus 1 quantity squared plus 1. So that means I'm going to let x plus 1 equal 1 times tangent theta. Hopefully you recognize that case. And then dx is secant squared theta, d theta. So now I'm going to rewrite this integral all in terms of thetas. So we're going to have here integral. First, let's rewrite it with the square completed. X plus 1 squared plus 1 dx. And then this is going to be, remember, dx was secant squared theta, d theta. X plus 1 is tangent theta, so we're going to have tangent squared theta plus 1 in the denominator. But oh me, oh my, tangent squared theta plus 1, that's secant squared. So this is integral secant squared theta divided by secant squared theta d theta. So you're just integrating d theta, or 1 d theta, which is theta plus c2. And remember, I have to rewrite this in terms of the original variable, in which case that means theta equals tan inverse of x plus 1. So this is going to be tan inverse of x plus 1 plus c2. Alternatively, you wouldn't need to do the trig sub if you could skip this. You're like, now you're telling me. Yes, I'm telling you now. Alternatively, you could not do the trig sub if you just noticed you did a little u sub in your head for regular old tan inverse. Let u equal x plus 1. Du would be dx. So you just make the argument x plus 1, a is 1, and call it a day and skip all that. Okay, that's totally acceptable. All right, integral number 3. Moving along. What was integral number 3? Integral number 3 was x plus 1 over x squared plus 2x plus 2 squared dx. And remember, we already found earlier that 1/2 du was going to equal x plus 1 dx. Remember, we were letting u equal x squared plus 2x plus 2. So this one's just a little different because we have that squared term in the denominator. So what does that mean for us? We have 1/2 integral 1 over u squared du. So antiderivative is going to be negative 1 over u, correct? So I have negative 1/2 times 1 over u plus c3. And then u was x squared plus 2x plus 2. So I have negative 1/2 times 1 over x squared plus 2x plus 2 plus c3. Okay, almost there. We are in the home stretch. Integral number 4. Voila. 4 is integral of 3 over x squared plus 2x plus 2 squared dx. Okay, I said this one was going to be a trig sub again, which means we need to complete the square in the denominator. So remember, we can write this as x squared plus 2x plus 1 plus 1, and this is all squared. So you can't do that little shortcut straight to tan inverse. I'm so sorry. This is going to be x plus 1 squared plus 1 all squared. So we are going to let x plus 1 equal 1 times tangent theta. So same sub as last time, it's just going to work out differently. Dx is going to be secant squared theta d theta. Now from here, let's rewrite everything in terms of theta. Let's take the 3 outside. And then dx is secant squared theta d theta. And then in the denominator, I'm going to have tangent squared theta plus 1, all of that squared. Tan squared theta plus 1 squared. Well, remember, tan squared theta plus 1, that's secant squared theta. So I have secant to the 4th theta in the denominator, basically. So let's write this out. We have 3 times the integral secant squared theta d theta over secant to the 4th theta d theta. So that's going to cancel out. Then I just have secant squared theta in the denominator. But 1 over secant squared theta is cosine squared theta. So this is 3 times the integral. Oh, I'm sorry, there should not be a d theta there. Get rid of that. 3 times the integral of cosine squared theta d theta. All right. Now let's think. How do we antidifferentiate cosine squared theta? Oh, that's right. We use the half angle identity. So I'm going to have 1/2. Let's take the 1/2 outside. So we've got 3/2 integral 1 plus cosine 2 theta d theta. Now let's go ahead and antidifferentiate. So this is going to be 3/2 times theta plus, got to divide by that 2, so 1/2 sine 2 theta plus, you guessed it, C4. And then let's distribute that 3/2, so now I have 3/2 theta plus 3/4. And then since I need to rewrite everything with respect to x, I'm going to have to draw a triangle for theta, which means I got to use my double angle identity now and replace sine 2 theta with 2 sine theta cosine theta, and then we have plus C4. Okay, so it's triangle time. Remember, x plus 1 was equal to tangent of theta. So here's the triangle. Here's theta. So tangent theta's ratio of opposite over adjacent. Then that means this hypotenuse side is going to be x squared plus 2x plus 2, square root of all that. Okay, so first things first, we've got 3/2 times theta. Well, theta is just tan inverse of x plus 1 plus 3/4 times 2, that's 3/2. And then now I need sine of theta. So sine of theta is going to be the ratio of the opposite side over the hypotenuse. So that's going to be x plus 1 over radical x squared plus 2x plus 2 times cosine theta. So cosine theta is going to be adjacent over hypotenuse, 1 over radical x squared plus 2x plus 2 plus C4. Can we clean this up some more? I think so. So this is 3/2 tan inverse of x plus 1 plus 3/2. If I multiply the numerators across, I get x plus 1. And then I have the same expression in the denominator. If you multiply a radical by itself, then the radical goes away. So I just have x squared plus 2x plus 2 plus C4. Whew, you guys, we made it. We just have to put everything all together. Here we go. Time to take everything off the back burner and plate the dish. So we've got from that first integral, it was a 1/2 natural log, absolute value, x squared plus 2x plus 2. Do you remember doing it, or was it too long ago? You're like, I just can't even be bothered. Okay, so there's the first one, plus C1, but we're going to save that. You know what we like to do to make it look so snazzy. Plus, from the second one, remember I had to subtract. Second and fourth ones were negative. So I'm actually going to have minus tan inverse of x plus 1. Third integral came out to be a negative 1/2 times 1 over x squared plus 2x plus 2. And then last one, remember we had to subtract integral 4 as well. So I'm going to have minus 3/2 tan inverse of x plus 1 minus 3/2 times x plus 1 over x squared plus 2x plus 2 plus c. And I'll define c in a second because I'm noticing we can clean up a bit more, yeah? We've only got one natural log, so that's not what I'm talking about. 1/2 natural log. You do need the absolute values because I don't know that 2x is necessarily positive, okay? Look at this. Look at what's going on. I've got negative tan inverse of x plus 1 and a negative 3/2 inverse tangent of x plus 1. So I can combine those, negative 5/2 tan inverse of x plus 1. And then these two terms have the same denominator, 2 times x squared plus 2x plus 2. So if I combine the numerators, Check this out. This is -1. This is -3x minus 3. So it's all negative. So let me just factor out the negative. You have 3x and 4 left over. I'm making them positive though because I factored the negative out. And then we have 2 times x squared plus 2x plus 2 in the denominator plus c. And then you got to let everybody know what c is, where c is equal to c1 plus c2 plus c3 plus c4. Wow, wow, wow. This was a beast of a problem. But you know, when you're in Calculus 2, you can handle it. Just hold yourself to this high standard and say, I am capable. So I hope you enjoyed that one. I'm exhausted. So be sure to give this video a thumbs up. Subscribe if you haven't already. I would really appreciate your support. And we still have more integration techniques to learn, believe it or not. No, just kidding. We're just going to summarize in the next video. All right.